Hello, everybody. So today we're going to talk about classifying real numbers. Okay. So there's a diagram of the real number system once you get past the title of today's lesson and see that I'm your hero in mathematics. I might not be, but maybe hopefully by the end of the year I am, with all the knowledge and the learning that hopefully I help develop within you. But again, down below, there's a diagram of the real number system. Okay. And basically, any number I give you in this class is a real number. Now, remember, real numbers are numbers that you can physically graph on a number line. So you could physically represent or put the number on a number line. Um, we don't see non-real numbers in Algebra 1. Now, in Algebra 2, you'll learn what's called imaginary numbers and complex numbers. And the biggest things with those is that they have an I in them. So an imaginary number has the variable I in it to represent its imaginary, and then a complex number is a combination of a real number and a complex number. So again, in Algebra 1, any number you see is a real number. Now, the exceptions to that would be like you can't take the square root of a negative number. That wouldn't be a real number because you can't do it. But other than that, if we give you a number, it's a real number. Okay. But the definition of a real number is a number that could be graphed on a number line, and they're numbers that we use or can use in everyday life. Okay. Or the real world. Now, we're going to talk about some of these subsets tomorrow, but the main thing I want you to understand today is there's two main types of real numbers, excuse me. We have rational numbers and then we have irrational numbers. So what we're going to focus on today is understanding the difference between those two. So I just gave you a brief summary of what real numbers are. It's a joke I usually say in class, okay? Are you for real? I try to be cool, but I'm not cool. So um, remember, numbers that we use in everyday life are real numbers, or we can use in everyday life, and they can be graphed on a number line. So that includes anything you could think of: decimals, fractions, integers, whole numbers, positive and negative numbers. Those are all different types of real numbers. Okay? And as I addressed at the beginning of the lesson, not every single number in the world is a real number. We have what's called imaginary numbers. And believe it or not, this is kind of weird to say, imaginary numbers do have real world implications, even though they're imaginary. But we'll cover that more in Algebra 2, or you'll cover that more with your Algebra 2 teacher. So, um, not all numbers in the world are real numbers, but um, most are. Okay, but you'll talk about imaginary numbers and complex numbers in Algebra 2. But the major thing, let me go back, and it's a little tough to see there at the bottom, but any real number can be classified as either rational or irrational. So let's focus on what that means. Let me bring all this up here. So this is basically kind of like a table almost. Um, so let's focus on the left-hand side here, rational numbers. Rational numbers are numbers that can be expressed or written as fractions or as a fraction. So any number that can be written as a fraction is a rational number. Now, as decimals, rational numbers either terminate, meaning they stop or come to an end, or they have a repeating pattern in them. For example, 1.333, repeating. In math, you put a bar over top, maybe one of those numbers, or the place value, or the place values that repeat, right? That would be a rational number. Now, an irrational number, that cannot be written as a fraction. So you cannot take a decimal that's irrational and represent it as a fraction. Okay? Now, as decimals, irrational numbers do not terminate and they do not repeat. So what that means is that basically it's a number that goes on forever and has no repeating pattern in it. That is an irrational number. Okay? So let's look at some of these examples really quick, whether they're rational or irrational. And I'll do a couple more examples after this because I could write on the screen. So the first one here is 3/4. Well, that's rational because it's a fraction, right? So it's a rational number. Okay. Now I have the second one, 3.141592654. I don't know if you recognize that because in the middle school you probably rounded it, but that's actually what's called pi. And notice that the number has no pattern in it, but it goes on forever. The dots mean that it goes on forever. So since this number has no pattern in it and goes on forever, it's an irrational number. Okay? -4. That's actually rational. Now, you might have a different justification than I'm saying right now, but I'm focusing on the definition of rational and irrational. Some people might say, well, -4 is an integer, so therefore it's rational. That is true. But going based off the definition of rational and irrational, -4 is rational because it can be written as a fraction. How? You could put it as -4 over 1. Any number, any integer, you could take that integer and put it over 1. So therefore, it can be written as a fraction. So it's rational. Now, you could also write that as -4.0, right? So since it stops, the decimal stops, it's rational. Along those same lines, 0.56. That is rational because it terminates or stops. Any decimal that comes to an end at some point is rational. Okay, we could actually represent this number as a fraction as well. Okay, what it would actually be, you would do 56 over 100 and then reduce it. But I'm getting a little, maybe that's details you don't need right now, but certainly some good math insight. Okay. The next one, 3.44 repeating. That is rational. Why is it rational? Because it has a repeating pattern. So rational numbers as decimals, they either terminate or they have a repeating pattern in them. Okay? So 3.44 repeating is rational. Also, the next one, 10.45 repeating. That is also rational because it has a repeating pattern. Okay? 0. Rational, I could write that as 0.0 or 0 over 1. The next number, 5.613490134. Irrational. Why? No repeating pattern and it goes on forever. And the last one is square roots. Well, that gets a little tricky. Here's what I'll say. The square root of a number is usually irrational. Okay? But sometimes it's rational. Where would it be rational? When you take the square root of a perfect square number. So let me address that right now. So let me go into Paint here. Okay, so let's say we have the square root. I just want to make sure I can write here again. The square root of 9. Well, the square root of 9, since 9 is a perfect square, and we talked about this a bit in the last lesson, that's equal to 3. So that is actually rational, right? But then we have the square root of 10. Well, there's no integer times itself that will give you an answer of 10. So if you have your calculator, go ahead and take this out because it'd be very, very difficult to get the exact answer without a calculator. But if you type this in your calculator, what your calculator says is 3.16227766 and it stops. But what that means is that it goes on forever because your calculator runs out of space. And maybe you might have a calculator that gives a couple more answers. But if you look at this number, even though it might look like there's something repeating, it doesn't. There's no repeating pattern in it. That's irrational. Okay, then we do the square root of 11. Type that in your calculator. And when you do that, you get 3.31662479. And now it stops in your calculator, but your calculator runs out of space. this actually goes on forever. Square root of 12. Type that in your calculator. Hopefully you're starting to get my point. We have 3.461. Get rid of some of these adds. 4101615. And again, your calculator runs out of space, so it stops, but that goes on forever. So hopefully you're seeing my point. Unless your number underneath the square root is a perfect square, well, any perfect square, we take the square root of it, it's rational. But if it's not a perfect square, it's irrational. Okay? So square roots get a little tricky because if it's not a perfect square, it's going to be irrational. But if the number you're taking the square root of is a perfect square, that's rational. So the square root of 16, that's 4, right? That's actually rational. The square root of 25 is actually 5. That's rational. But if I take the square root of any number in between these, like the square root of 17, square root of 18, etc., those are all irrational. So hopefully that helps you. Again, rational numbers are numbers that could be written as a fraction or as a decimal. They either terminate or repeat. So for example, 1/3 is a rational number because it's a fraction. 6 is a rational number because it's a fraction, 6/1. You wouldn't see it like that, but I could make it a fraction, right? Or I could write it as 6.0, making it a terminating decimal, okay? The number pi, and we saw a little bit differently in the previous slide. If you see that symbol, guess what? Irrational, okay? Pi is irrational. Or if you see any operation going on in the pi, that is also irrational, okay? Or a decimal that goes on forever and has no pattern, that's also irrational. Now, if I have a number like 5.131313 with dots on the end, well, guess what? That's actually rational because it has a repeating pattern in it. Okay? So hopefully by going over some of those examples, it helped you understand the difference between rational and irrational. Any real number could be classified as either rational or irrational. Okay? Tomorrow we'll talk more about the other classifications for rational numbers. So thank you very much for your attention. I hope you guys have a fantastic day.